Hello everyone. In today's lecture we will talk about different type of mass analyzers which are used in various type of mass spectrometers. In earlier lectures we have discussed about a component of a typical mass spectrometer where you have inlet which use a sample in solid form or liquid form in gaseous state and inject into ion source. So ion source basically analyte and then send it to mass filter or analyzer where the objective is to sort ions on the basis of their M by Z values, and that is performed by mass analyzers. Then those ions which are sorted by mass analyzers, they are detected by detector, and eventually finally we see a mass spectra. There are different type of methods which are used in order to employ into ionization process of different type of analytes. Those also we have covered in a separate lecture about different methods of ionization in mass spectrometry. Then in today's lecture we will talk about different type of mass analyzer. There are different type of mass analyzers which are used, and each and every mass analyzer is compatible to some or other method of ionization in mass spectroscopy. So there are two types of mass analyzers. You call them continuous analyzer or pulsed analyzer. Continuous analyzers are those where these analyzer continuously keep sorting and sorting ions and keep sending them to the detector. For example, in case of quadrupole analyzer or even in magnetic sector analyzers. The second type of analyzers, which they collect an entire mass spectrum from a single pulse of ion. A single pulse of ion is given to the analyzer, and that single pulse is resolved into different components of a mass spectra, and that happens in case of time of flight analyzer or ion traps or ion cyclotron types. The use of a mass analyzer is filtering and sorting of ions which are coming from ion source after ionizing analyte into a gaseous state, and it's a filter and sort ions on the basis of their mass to charge ratio. That's also called M by Z values, and there are different types of analyzers which are available in different spectrometers. For example, the simplest one is magnetic sector or quadrupole mass filters. Then you have triple-quadrupole also, then time of flight analyzers, then Fourier transform ion cyclotron resonance FTICR type of mass analyzers, and Orbitrap mass analyzers. In fact, in case of FTICR and Orbitrap, along with the sorting ions on the basis of M by Z, they also detect ions. So it's a combined detector and analyzer. Both components are combined in Fourier transform ion cyclotron resonance and Orbitrap mass analyzers. The simplest type of analyzer is a magnetic sector analyzer, where the ion of beam is subjected under the influence of a magnetic field. So you have a magnetic field, and the beam of ions, when it passes through the strong magnetic field, it doesn't go into the straight line, rather it is deflected. That we have also discussed this in detail in the principle of mass spectroscopy in earlier lectures. So for example, you have this ion, and this is accelerated into magnetic field. So instead of going into a straight line, the trajectory is bent into a circular orbit. So it moves something like this. So the force applied on the ion under magnetic field is equal to QEB sine theta. Sine theta would be 1 here, because the magnetic force is perpendicular with respect to movement of the ion. So QEB, and this QEB force is converted into centripetal force, because this ion here is acquiring a circular orbit. So that would be equal to mv square upon r. So QEB is converted into centripetal force. From this equation we can derive the value of radius of this circle which is adopted by this ion under magnetic field, and this radius would be equal to mv upon qb. So radius basically tells you about how much deflection an ion is going through under a certain magnetic field. Lesser radius means stronger deflection, and higher radius means lesser deflection in the magnetic field. And because these ions, they are also accelerated, providing some current. So in that way, the kinetic energy half mv square would be equal to qv, where q is the charge on the ion and v is the voltage applied from outside. So from here, the value of small v, which is velocity, that can be calculated. And if you replace this value v into radius r, so radius would be actually equal to 1 upon b into under root 2 mv upon q. So the radius of this ion under magnetic field is inversely dependent on B. B is strength of the magnetic field here. So if you increase magnetic field strength, radius will be small. It means the deflection would be more. Or it also depends on m by q or m by z, mass to charge ratio. If smaller is the ion, means m by z or m by q is small, the radius will be small. That's what we say, the lighter the ion, the more deflection, because lighter ion means m by z or m by q is small, so the radius will be small, so it will deflect more under the magnetic field. Conversely, if m by z is high for an ion, the deflection would be least, the radius would be more. So this kind of a magnetic sector analyzer, they basically measure deflection of the ions in order to sort them based on their m by z values. So in such system, the magnetic field is varied from low to high, so that all the ions, ionic beam containing different m by z values, they are separated on the basis of m by z. If you have, for example, if you have a constant magnetic field, you see here there are three different type of ions. You call them stream A, stream B and stream C. So in these cases, stream A is deflected maximum. It has a small radius of deflection, whereas stream C, the red one, the radius is very largest, so the deflection is least here. So only B beam, the green color beam, is the one which is being detected under this magnetic field by the detector. So in order to detect beam A and beam C, you need to vary magnetic field. If you want to detect beam A, which is deflected most, you need to reduce the strength of magnetic field. And if you want to detect the beam C, you need to increase the strength of magnetic field. That's why in these type of analyzers, the magnetic field is varied, so that all the ions having different m by z values, they are detected one after another. Then you have double focusing mass analyzer, which are basically combination of electrostatic analyzer and the magnetic analyzer. So additionally here, the electric sector focuses ion with respect to difference in kinetic energy, so that they may have, as they exit the source region. So when they are exiting from the source region, so based on their kinetic energy, electrostatic analyzer that focus them, and then the magnetic analyzer basically on the basis of their deflection, it sort them on the basis of their m by z values. And depending on the geometry of these electrostatic and magnetic analyzers, they are of two types. You call them Near-Johnson geometry and you have Matusch-Herzog geometry. They give better resolution than magnetic sector alone. Quadrupole mass filters, they consist of 4 parallel rods, and this mass sorting depends on ion motion resulting from simultaneously applied constant DC and radio frequency electric fields. So alternative rods here, they are kept as at DC and RF electric field, and when these ions they pass through between these poles, the sorting of these ions that occurs by changing the field strength, so that a particular m by z ion is passed through and reached to the detector. So these kind of quadrupole mass filters, they provide lower resolution in comparison to double focusing instruments, but same time they are the cheapest mass analyzers available, and they can be easily interfaced to various inlet systems. Then triple quadrupole mass filters are also used. For example, in case of tandem mass spectroscopy, there are 3 quadrupole in tandem which are used. You call them Q1, Q2 and Q3. The ions, they are injected into Q1, they are sorted by Q1, and after sorting ions based on their M by Z values, those ions are sent to Q2. Q2 here is basically a collision induced dissociation cell, is called CID cell, where inert gas like nitrogen or argon, they are used to collide with the analytes, with the ions which are coming from Q1. As a result, those analytes get fragmented, and those fragmentation pattern, those fragmented daughter ions, they are then detected by Q3 quadrupole, and Q3 give you a mass spectra of fragmented ion. So this kind of QMS triple quadrupole is used in case of when you want to fragment molecule into pieces, and that's where when you need to get a structure information about the molecule. For example, in case of sequencing of peptides, so those peptides are broken down into pieces. That's what is done in case of tandem mass spectroscopy, and those pieces, those are analyzed by the third quadrupole here, and that give you idea about the structure information about that peptide. Similarly, if you want to identify, if you want to know the structure of nucleotide sequencing you want to do, you can use the same kind of technique. Or even identification of compounds, to get structural information about a compound, you use MSMS, where you have a triple quadrupole in tandem. Time of flight TOF analyzer, they are also very common type of analyzers which are used in proteomic studies. And here you have a time of flight tube, and the flight time of ions from one end of the tube to the detector is calculated, and from that flight time, this flight time is converted into M by Z of ions. So this TOF, they have very high sensitivity, generally around 5 fermetomole, and that much amount is there, which is when you do proteomic studies and stain a 2-dimensional gel with the silver staining, so you get the amount of protein in that range. So that's very much compatible with the proteomic experiment also, because in case of proteomics, when you detect protein, the amount of the protein is too little. So in order to detect that, identify that, you require this kind of analyzer to have this sensitivity. And they have very high sensitivity and very rapid scanning, and they also provide mass data for very high, almost around 500 kilodalton proteins can be analyzed using TOF analyzers. Then the separation in TOF, that occurs by virtue of the difference in flight time of ions, and that flight time difference is basically depend on M by Z of those ions. For example, the potential energy of ion here would be ZeV, where Z is amount of charge, E is the charge, and V is the voltage applied. And this potential energy is actually converted in kinetic energy in the TOF, that is half mv square. So if you keep them together, half mv square is kinetic energy, m is mass, and v is the velocity of those ions. So if you keep them together, you will see the value of v is equal to under root 2 ZeV upon m. And from here, so we see that velocity of ion is inversely proportional to the mass. It means if you have high mass, the velocity will be less, and time taken to reach to the detector by those ions will be more. And in contrast, if you have a smaller ion, if your M by Z is less, or you have mass is less, in that case velocity will be more, and more velocity means it will take lesser time to reach to the detector. So from this equation we can calculate the time taken as well. The time taken by ions to reach detector is equal to d upon v. D is the distance traveled, that is basically length of the TOF tube, and v is the velocity. So if you replace the value of v from here, and see that t is equal to d under root m upon 2 ZeV. So from here the value of m by z can be calculated, and that is m by z is equal to 2 EV into T upon D whole square. So you see here EV is known, distance D is known. So only if you can calculate T, m by z can be calculated. So just by knowing the time of flight of ions, m by z value can be calculated, and that's how a graph, the spectra can be formed. Mass spectra can be formed from here. There are two types of TOF tube. One is linear TOF tube. In linear TOF tube, ions enter to one end and they are detected in opposite direction of the ion source, where you have some resolution. Then you have another which is very common these days, that's a reflectron or reflector time of flight tube. In reflectron, you have ion mirror, and from this ion mirror, these ions are reflected. They are reflected and collected in the same direction. Detector is located at the same direction of the ion source. And basically this reflectron, it comprised of two zones. In the first is the shortest one, where ions are strongly decelerated. Here the ions are in accelerated state. But in reflectron, first deceleration occurs and then they penetrate a longer second zone. The second zone is relatively longer, and they are progressively slowed down here. It's a zero field zone. There is no field applied here. As a result, all the ions, they come together having same m by z values, and that is required because all the ions, when they exit from the ion source, despite of having same m by z value, they may not have same identical kinetic energy. So in order to put them together to improve resolution, reflectron is required. So reflectron basically slow down ions which are having high kinetic energy in comparison to the low kinetic energy analytes ions with the same m by z values. So that's why it's kind of stacking of ions before they are detected, so that all the ions, irrespective of their difference in kinetic energy, all the ions which have same m by z, they are collected together, so that the peak you get, they are more sharp, they are more resolved. So in comparison to the linear TOF tube, you have much better resolution in case of a reflectron. This is one of the very advanced system to sort ions in mass spectrometer, that's called Fourier transform ion cyclotron resonance, FTICR type of analyzers. FTICR is the highest resolution mass analyzer available so far, and they use a strong magnetic field to cause ions to go into a circular orbit. We know that when you have accelerated ion and you pass through under magnetic influence, it doesn't go into the straight line, but it bend into a circular trajectory. And the radius of that circular trajectory would depend on m by z. So R is equal to mv upon zh, where m is mass, v is the velocity, z is the charge, and h is magnetic field here, which is kept constant. So in this ICR cell, ion cyclotron resonance cell, is basically a cubical or cylindrical cell where there are 4 plates. You have 2 excitation plates and you have 2 detection plates. And this cell is kept as very high magnetic field. So when a beam of ion is injected into the cell, these ions, they are pulled depending on the charge towards opposite electrode. But because same time you have magnetic field also applied, so they start circulating into a orbit, circular orbit, due to presence of the magnetic field. That's what happens. So and then these ions, they are detected by the detector, because moving ions, when they come to the detector electrode, they produce current, and that current is measured in ICR cell. So basically m by z can be measured in ICR by measuring angular velocity of the ion. This angular velocity or cyclotron angular. Cyclotron is a machine where you can accelerate ion by applying magnetic field and electric field together. So in this the angular velocity, cyclotron angular velocity of ions, omega c is equal to zh upon m, where z is the charge, h is magnetic field, and m is mass of those ions. So So the motion, the angular velocity or angular frequency is dependent basically on m by z of those ions. So somehow if you can determine the frequency, angular frequency of these ions which are circulating into the orbit in a ICR cell, you can determine m by z also. And this is done by detecting tiny current induced by the ion as they pass close to the detector plates. For example, you have these two detector plates, and when you enter this ion between these detector plate, of course, which are kept under high magnetic field, so this ion, they start circulating into an orbit, and when these ions come close to detector plate, because they charged, accelerated charged ion, so it induce current into this detector plate. That's called image current. So image current is detected, and this image current is dependent on a cyclotron frequency of this ion, and cyclotron frequency is dependent on m by z. So that's how m by z is calculated. So the first spectra you get from here is a time dependent, time based spectra, where voltage is calculated due to presence of ion in proximity of the detection plate, and you get a sine wave spectra in fact. But there is one issue, because for example, if you have a detector plate here, so initially when these ions enter into ICR cell, their frequency is too small to be detected by detector plate. They are oscillating in a smaller orbit here, for example here. So in order to get these detected, they should come close to the detector plate. So, and that is done by exciting these ions with the RF radio frequency pulse. So if radio frequency pulse is given from outside, these ions get excited, and that would depend on their cyclotron frequency. So when RF frequency is in resonance with the cyclotron frequency of these ions, they absorb RF frequency and get excited. As a result, they start orbiting into a larger circle, for example here, and eventually they come close to the detector plate. And when they come close to a detector plate, the change in current is measured with respect to time. But when you remove the RF pulse, radio frequency is removed, they go back to the original state and they start oscillating with the cyclotron, their original cyclotron frequencies. That's why this data goes down. You see the sine wave goes down eventually with time. So this is called in fact free induction decay, or FID, or transient or interferogram, and this consists of a superposition of sine waves. For example, here there is only one type of ion, so you got one sine wave only. If there are multiple ions in the sample, you will get multiple sine waves which are superimposed on each other. So eventually you have very complex spectra which is converted into frequency domain by Fourier transformation. So something like this, if you have many different type of ions in your sample, the transient data is very complex. So these sine waves are converted into frequency by Fourier transformation. So each wave is splitted, each wave is converted into frequency domain, and this frequency data is eventually by calibration, it is matched with m by z. So your final data you have is m by z versus abundance. So this is mass spectra, and we know that in earlier lecture we have discussed the m by z data can be used in deconvolution in order to get mass of the analyte. Another very recent modern type of mass analyzer is called Orbitrap. It has a similar principle as like FTICR. The only difference here is that you don't use magnetic field here. Instead, there are 3 electrodes. The one central electrode which is a spindle shape, and there are 2 cup shape electrode which surround the central electrode. So when ions are injected into this cell in Orbitrap, they start oscillating around the central central electrode here in a spindle way, in a spiral way. So, and the detection of these ions occurs at the same way like it is done in FTICR. First transient data is observed. That transient time based data is converted eventually into M by Z data using Fourier transformation. And this axial frequency of these ions when they are circulating around central electrode is equal to under root k, where k is a constant based on machine, divided by M by Q or M by Z. So basically this axial frequency is the one which is measured here. In case of FTICR, that was cyclotron frequency, but here you have axial frequency. And the Orbitrap differ from FTIR by absence of a magnetic field, hence has a significantly slower decrease of resolving power with increasing M by Z. So when you increase M by Z, the resolving power is very slowly decreases in this case in comparison to FTICR. So in operation, ions are stored in a linear trap. So they must be coming from some ion source. Here, for example, this is ESI is very compatible with this kind of mass analyzer, electrospray ionization method. Then these ions are stored and then they are basically axially ejected to the C trap. This is C trap. And the function of C trap is to make packets of those ions and send them to Orbitrap. So these ions are squeezed into a small cloud and injected into the Orbitrap here. This is Orbitrap. And here these ions are electrostatically trapped around the middle spindle electrode while rotating around the electrode and performing axial oscillation. And while this is oscillating around this middle electrode, the change in current potential in the outer electrode is measured with respect to time. So this oscillating ion induces an image current into the outer half of the Orbitrap, which are two electrodes outside the cup-shaped electrode, and it can be detected using a differential amplifier. So you get this kind of data, is a sine wave data, which is coming from outside electrode, two outside electrodes. So ions of only one mass generate one sine wave, but when you have multiple ions, you get a complex spectra of sine waves superimposed on each other. And this spectra is likewise in case of FTICR, this is converted into frequency and then eventually to M by Z spectra. If you compare ICR type of mass analyzer, they are most expensive one in comparison to quadrupole, magnetic sector and time of flight. Quadrupole are the cheapest one, and the size wise also ICR, they are bigger in size, they are more expensive, they give highest resolution in fact in comparison to all other mass analyzers, and efficiency of ion separation is also maximum in case of ICR type of mass analyzer. In fact, a single ion can be separated and analyzed by ICR based MS mass spectrometers.